Thank you for the introduction. I will say that when you'll see some of the information here I present from NESDIS, I take very little credit for the past accomplishments. I take no credit for the past accomplishments. I've been at NESDIS now for 5 months. So I will take ownership of the future problems that we may create, but not of the past accomplishments, which are many. So thank you for the opportunity and the honor to speak here today. This is a great crowd. I've walked through and met with and seen many of you. Many of you I know from my previous career when I was at NASA headquarters and NASA overall. So I'm happy to be able to talk here a little bit about what we're doing at NESDIS and NOAA and trying to address the topic of this symposium, which is on the cusp, what's next. So let's see if I get this right. Apparently, which side? I was trying to get the roll of the wheel there. Oh, I guess you're going to, we'll see. So I had to look up what on the cusp was. I use it a lot, but I looked up in the dictionary and found out what it was, and I thought it was interesting. The first one they mentioned is a technology example. Sort of the transition marks the beginning of something. It also marks the threshold or the verge of something happening. But also the last one is the dividing line between two states, two conditions or categories. So the beginning of something is always very positive, but often, as you look at the example there, the transistor was on the cusp of a new age of electronics. Well, that's all exciting if you're in transistors, but if you're building vacuum tubes, it was a very different kind of experience for you being on the cusp. So we'll see a little bit going forward. The trend changes bring a lot of opportunity, but they also bring some risks and you have to watch out what you're going to get in your changes now. Let me see if I can. So go ahead, next slide. So I was looking, and this is part of the history which I don't own, but I take credit for. We have many generations. You know, what have we done within NOAA and in the Weather Service, even before NOAA, and go ahead and click the next one, over the last 50 years. NASA is 50 years old. NOAA is only about 40 years old, but we try to look at it in terms of generational changes that you see. And we started off the decades of the 60s. It was NASA flying the satellites. NOAA didn't become an agency until the early 70s, conglomeration of a bunch of other activities we brought together. But in each step, and the first one, it was just what can we do from space and how cool and wonderful this is. The next step, we started to go to slightly larger satellites. We had our first 3-axis stabilized geostationary bird in the 80s time frame. And at that point, both in the LEO and the GEO, we started looking at what do we do next after this. One of the realities of satellite development, particularly for operational satellites, is it takes 10 to 15, sometimes 20 years to turn an idea into an implemented satellite. Next one. And sometimes that can be disrupted by other cusps. NPOS is one that kind of caused a major disruption in the middle, because that was supposed to be a change in the whole paradigm. You're not going to have multiple weather services, you're going to have one. It's going to do everything for everybody. Kind of like when the shuttle was going to launch everything for a few dollars a pound. And we had to live through that era for a while until we devolved from that. Go ahead and click again. And in the 2000s, we were sort of flying out, if you would, the LEO satellites, the NOAA 15, 16, 17, which are up in orbit now, 18, 19, direct orbit insertion. Those are the technologies we've been flying for 15 or 20 or 30 years. They're capable. We have developed an entire weather service which lives on those data products, and it's very functional and it's capable as well. But we have to think about what's next. It was around the NPOS start, the late 90s, when we started looking at the next generation, which we're now seeing wasn't launched until 2010, when JPSS, SUMI NPP, was first launched. But that was a real transitional change. It was a significant change. The first data set from SUMI in a month provided more data than was in the entire archives for all the previous generations of NOAA satellites. So that was a big change, and we weren't ready for it. It took a while to figure out how to swallow this pill and how to make it a regular digestive system and move stuff through in a regular process. SUMI is that NASA and NOAA built together. It's been essential in making us ready for JPSS-1. Click again. So at 2020, we're going to be flying the JPSS series. That's the series of satellites that we built in '95. We're launching all the way up through the mid-20s, and that will provide a service for us through the late 30s if things work well. It has new capabilities with new instruments such as CRIS, VIRS, and ATMS, and we're going to ride that instrument wave for the next 15 years, next 20 years. And on the GOES on the geostationary, it's the same approach. We have a new capability on GOES ABI and the global mapper, iLightning mapper, which have not been flown with the quality. The GOES ABI is an evolution, but a significant step forward. The Lightning mapper is the first time. So that was a transition to the next generation. So we're now, go ahead and click again, we have to figure out what we're going to do next. Do we want to continue to build JPSS forever? Do we want to have one big satellite that has all the capabilities in it? Do we do one big GOES, which these satellites are not cheap. They're on the order of $2 billion a pop. Ground system, when you add it all up, these are very significant investments in both in satellites and in ground systems. So we need to be careful when we go to this transition to the next generation that we we are aware of what we've already invested in, but we don't get so stuck in our investments that we just keep building the same thing until somebody comes up with a transistor to replace our vacuum tubes here. So we have to look forward to what we're going to do. So click again. So this is the paradigm we've been operating under for the past 20 to 25 years. This is sort of the motto or the vision. It was 2 orbits, 1 mission, the 1 mission being weather for the nation, 2 orbits being a polar LEO and a geostationary. And we have a piece of it, as on the previous chart showed over time, we collaborate with the Europeans and with the Japanese. We carve up the world, so to speak, for the geostationary to get the full global view. We carve up the clock from the morning, early morning, mid-morning, early afternoon orbit to get the repeat coverage. It's a big constellation, requires many people. But this is where we have been and where we expect to be until the early 2030s. Click again. So, and it's been productive for us. We have the LEO and GEO platforms provide a stable constellation, and it's a comfortable zone, even though it's expensive, it's reliable, it's productive, and we have an entire production system in terms of weather, the National Weather Service, the numerical weather modeling, the programs, which produce accurate and increasingly more accurate weather products and services. But now is the time to start looking at what we're going to do next. Now, along with these, we add other things that we have to think about how we would, with this backbone established, what do we add to this to bring the next generation forward? And then I just have a couple of charts. And we can just skip through these. This is the POSE, click one more time, the polar flyout chart, which shows through about 2038, the JPSS satellites that are in the current president's budget will be flying through around 2038, barring any failure of a satellite. Next, and click again. For the GOES missions, click one more there. We have 3 satellites in orbit, and we have 4 in the pipeline, 1 launching a year from now, March of 16 for GOES-R. This is a big milestone for us at NOAA. And these will also provide the geostationary platform for us through the next 20 years, through the 20 to 20-some years. And this is the backbone that I mentioned before. Go ahead, next. And it is larger than that. It is a much larger system we operate. It's not just our satellites that I just mentioned. We use NASA research satellites. We use ESA research satellites on a regular basis. In fact, we were using NASA EOS satellite measurements from AIRS on our products for many years, and we still do from the AURA and Aqua and Terra satellites. EUMETSAT and JMA, they have our operational satellites, and now the EC Sentinel series have started to come in there with a potential transformational capability bringing into us and what we're going to do with it and how we use those data sets as well. So it's a much larger constellation that we have here, and a change in any one of these elements can have a profound effect on all of the other elements. So we have to be sensitive to what may, for example, when the Sentinel data come in, what does that mean to us? We can ignore it and act like it doesn't exist, and then other people will see products come out by somebody else using them, or we can take advantage of it and figure out how we adapt our system to better use the incoming new data as it comes. Next. This is the other piece of the paradigm here, how we do our data processing, what we do with the measurements we have. So our current one, we have all of our satellites that NOAA builds up on the upper left. The European or the contributed satellites, either not contributed, but the measurements that we use from the Europeans, from NASA, from the Japanese, from the European community, ESA. We take all of those data, we process it through our operations facility. There's a significant investment that we have at NSOF, which is the NOAA Satellite Ops Facility, and then numerical weather modeling with the NWS, et cetera, which takes that significant stream of data flow and processes a series, hundreds of products and services from minute latency to months and years and climate data sets that are all developed into this pipeline. So this is an example where you have a significant pipeline of many, many different organizations developed over 30 to 40 years, and then you have new technologies and new investments coming in, and how is that going to affect the pipeline, and how do we need to change the pipeline to adapt to that? Imagine you're building film or camera film 50 years ago. I've got that whole production line, I got to be ready for something, and I don't know what that is, but I got this investment, and how do I make it usable for the future? Next slide. So how do we go beyond the 1 mission, 2 orbits? One of the things is we're always going to be launching in LEO. There's a certain value to LEO orbits, the temporal resolution, the high repeat cycle, and we're going to go to GEO because of the stare and the stand and stare of its capabilities. But we're going to get beyond just we're a 130 orbit crossing time for JPSS, and that's what we do. So the first thing, we're still going to have the baseline, but we're going to add other measurements to that constellation. Right now, we already have the Cosmic 1 set of measurements. That is a radio occultation set built by the Air Force, Taiwan, and NSF. We're augmenting that with Cosmic 2, which is a repeat with a 12-satellite constellation to do that as well. These are not in any stationary orbit. These are scattered all around the globe for complete coverage. And those provide a set of microwave sound, different atmospheric sounding measurements, which are complementary to and additional to the existing ones we get from our baseline satellites. So that's broadening the concept of one orbit. The one orbit has gone from one crossing time orbit to a lower Earth orbit. Similarly, in our new proposals, we're looking at different technologies that might achieve some of our most critical measurements, and that would be atmospheric sounding, which is one of the most important ones for us that we get from ATMS and CRIS, with what we've proposed is a nanosatellite approach of a microwave radiometer, EON MW, we're calling EON microwave. And that's trying to step into the CubeSat approach, which is where there are technologies that can be miniaturized, can they serve our needs? We can't say they will, but we can't say they won't until we explore them, try and find out. So that's one of the ones we're doing in this next generation is to add, right now, this is a 2019 launch target, to add that to our existing constellation. And for the there may be other small sats hosted payloads, capabilities which weren't there 10 years ago, were definitely not there 20 years ago, and there weren't in any trades. If you look at a trade space that was developed for the JPSS series, there was no consideration that we're going to have, I don't think so anyway, at least didn't get very far, we're going to have hosted payloads, and we're going to have small sats covering our measurements. They are there now, and they have to be included in our trade space analysis. From geostationary, it's a little bit more complex. It's harder to get to GEO than it is to get to LEO. We still have the GOES-R series, but there are different architectures that are included as well, such as hosted payloads. We have a proof of an example that's worked once for the CHIPS satellite from the DoD. NASA is trying a couple of hosted payload approaches, one from GEO and maybe some from low Earth orbit as well. That may be a viable approach for some of our major measurements. If you look at the GOES-R satellite, for example, it is not an Earth science imaging satellite. It's an Earth science imaging satellite. It's a radio, it's a communications satellite with a massive rebroadcast capability. It's a bunch of things folded into one. Is it possible to separate those? Is it possible to find different ways to achieve different elements? That's going to be one of the ways we look at it, because there's a commercial communications market out there which can do it maybe much more effectively and with higher reliability and redundancy than we could do by buying it the government way only. And another part is alternative orbits, not just LEO, not just GEO. Are we looking at MEO orbits potentially? Would we be looking at a polar orbit or a Molniya orbit, they're called, or sometimes just the Arctic orbit? Because there's a lot of interest in what's going to happen in the Arctic over the next 20 years. Having the ability to stand and stare at that is going to be very, very helpful. We don't have that right now. Click one more. And added to this is also the commercial capabilities. There is a lot of advocacy out there, from mostly self-advocacy from those who want to sell the data, for commercial capabilities that can replace or substitute or enhance the measurements that we already make. To say that they are not good enough now may be true, but that doesn't mean they're not good enough ever. And we need to be ready to look at and find a path to evaluate whether they will ever meet our needs, and if so, what can we do to make them a little bit more effective today and tomorrow and 5 years from now so they might meet our needs. Next. So as far as the commercial side of the house goes, we're trying to address that. It's a technical, it's a scientific and a modeling, and it's a policy question, a challenge for us that we have at NOAA, is how do we engage these at the same time we do it in an open and transparent way. So we're working within NOAA to develop a policy at the NOAA level for how we would engage commercial services, but at the NESDIS level, it's more of a process. How do I talk to all the vendors? How do I communicate what our needs are and how we define a measurement, how we define an implementation, what the constraints are to the operating system down the road. It's not just the quality of the sounding, it's the form and function so it fits into our overall program and how the algorithms are built, et cetera. So we're developing that, and this year is going to be a key time for clarifying that and communicating that to the public. Next. So this is what we have now. It's a constellation of many. This is just a geo picture with many satellites in orbit. Go ahead and click again. And what we have in the future, what's the difference here is you see a bunch of little satellites potentially, microsats, CubeSats, small sats thrown in. Are we gonna, they're gonna be up there taking data. How we figure out to use them is going to be the challenge. And can they be useful for us? They're useful for many things. Can they be useful for the highly critical numerical weather products that we do? Next. And how would that fit into our data source? You saw this before. Click again if you would. So we look at where are these different assets coming in? Where do they fit in? They fit in during downlink if we have small. We might buy these satellites down at the bottom, and then we build them differently. They fit into our system, but we might also buy the data. Click one more. So it goes directly in. But do we want to buy data products, or do we want to buy raw data? There's a lot of resistance. When you think about the output of what we have, which is a weather forecast or an alert, we know we control the end-to-end flow. We know the instrument that was built. We know the algorithm that was written for it. We have the ground station. We control the provenance of the data from start to finish. So we can check and validate that, and if there's an error, we correct it. So we have to be very careful about the thought of using somebody else's checked and validated product and then using it in our presentation of what we go forward with. So whether or not we would ever buy products is problematic, is a challenge that we have to understand. But certainly the data where we can check and validate and truth check the data is a place where I think there is a ready now discussion about how we can integrate with the processes. So sort of in closing, a couple of minutes here on closing. So what are the challenges that we have to deal with? What community changes could change our operating paradigm? I've talked a little bit about what I think we need to be ready for, but sort of thinking of it in terms of access to space, data quality, and satellite technologies. I didn't bother to put policy on that. I've learned when I'm my 5 months at NOAA, I'd be really careful about talking about policy. That's not my job, and I get in trouble if I do. So we'll just talk about the hardware side of the house, which is my job. So click the first one. So access to space. There are a couple of these. We'll click these one at a time. What do we have now? We have big satellites, big rockets, and big money. They cost on the order of $100 to $200 million a shot. If we go back 10, 15 years from now, it could be $300 million a shot, according to our models. Click again. So we're looking at next generation, which might be 1/10 of that. Instead of 100 to 200 or $200 million, you might be talking about $20 million. Click again. We may see the threshold going down even more to, $2 to $5 million a pop. Click one more time. I don't think we'll get this far, down to a few dollars a pop. That's your CubeSat launch vehicle there on the far right. But if we change, we build our satellites to fit the launch vehicles. We'd say we don't, but we end up doing it. I got 10,000 kilograms to LEO anyway, why put a 500 kilogram satellite on that? It's going to cost me that. So you build a 5,000, 8,000 kilogram satellite, and that costs, the multipliers on cost and complexity go way up. If I had a launch vehicle at 1/10 or 1/50th of that $200 million, I have the ability to generate a satellite constellation that I can replenish at will. I can upgrade the technology. I can have a constellation which has higher temporal resolution, smaller swaths, but a larger integrated system. And it allows me then to be technically refreshing on a regular basis. So a big threshold in the next few years, 5 to 10 years, if we see this launch change, and I know Falcon is, the SpaceX is great in bringing this 200 down to 100. But the real change is going to be from 100 down to 10 or to 5. And that's going to make it a real transformational change in the way that we characterize our architectures and our observing structures to be able to deliver that. Now, the downstream impact of that is going to be great. It's going to be about how do we deal with all those different kinds of data. And that gets to the next question, is about data. Data quality, data ownership, and data integration and fusion. Right now, we have wide swath imagers. You get all the imaging at once. The data fusion is real simple. I just have VIIRS, which is 2,400 kilometers wide, and it's real easy. Or I have Landsat, which has the standard picture it's had for the last 30 years. You go into a different constellation with a different fit, go ahead and click, and you can see this is, you end up with a mix of different kinds of data sets and things. So when I look at the data mix that we have now, this is where you get into data ownership and data quality. On the data ownership side, it's public versus private. And one of the major issues that or paradigm, let me say, I call it a precept that we have, is our data are open and free. It's sort of it's a public good that we provide. The data that we take are open to everybody. And it's integral in all of our community MOUs and arrangements between the Europeans and all the spacefaring nations. We share our data, they share their data. We share our model results, they share theirs. There's no ownership, there's no exclusive ownership, so that we can all get better by comparison. Now, if we start buying data, then we have an issue here about, go ahead and click again. This is where the current NOAA sphere of operations are. Is a little bit into the proprietary private data. We buy some local data, but no global data. So we might buy some lightning data around airports. We might buy some radar data around airports for local mapping. But for our global, it's all public and free. And that's the place where we operate. Click again. If we start buying data, we're going to have to worry, is it owned? Is it trademark data? Is it controlled by the owner? Do we have it for limited use only? These are real issues that we have to address and deal with. Suppose that we get it for limited use and it predicts something that either doesn't happen or predicts it wrong and we have a problem. Then who's liable for it? We own it, we presented the data, so we have an issue there. So the ownership is real key, and we've been very careful about, and we've been very clear that it's a public good, and we want to continue to operate in a largely free and open space. But our objective, click one more here, is to move that line as far to the upper right as we can. Of course, if I were an industry side, I might have the arrows going the other way to move the line the other direction. So that's the dynamic, that's the dialogue we're having right now, and I expect us to have for the next 15 years as we try and define where there is a trade space for them. So after we get the data, click one more, we've got to make it usable. We've got to fuse these data together. We have different images, different slices of the data set, of the physics, and how do we take these and make an integrated whole Earth model, which is what we're really trying to do. Ultimately, almost all of our products rely on more than one measurement, whether it's in situ for calibration, or your ground calibration, or you're using an imager to map for cloud discrimination, and then you have a radar sounder, etc. Almost all of our products require multiple data sets. So the fusion of all these data is going to be even more complex when we take Sentinel data and now we merge it in with POSE data and we mix it with a GOES image, and all these have to be working together. So our ability to manipulate massive data sets from multiple different owners and provenances is going to be all the more important as we go forward. So you think about the investment we made in satellite technology, the investment we're going to have to make in data processing and data integration is going to be much larger and much more significant as we go forward. So, and finally then, in the technology side, click again, what are the satellite technologies I see that we might be using that might be useful and helpful for us? Next. This is the typical satellite that we build now. I talked about the big launch vehicle. That's what you put on a big launch vehicle. Those are little people. Those are not Lilliputians. Those are real people on the bottom there. So you're talking about something the size of a school bus, or two of them side by side and filled with lead. That's how big they are and how massive they are, and expensive. So next, and we're already looking at technologies which are tabletop size or washer machine size. We don't use these typically for our critical measurements because we put everything on one big bus. But the capabilities of these for pointing control and accuracy, for data downlink, for storage, are now comparable with what we had 5 years ago, 10 years ago when our big satellites. So the bottleneck had been the reliability, the data downlink capabilities are no longer there as a discriminator whether you go with a big one or a little one. It's still that launch vehicle is the one that's driving most of that in terms of the cost of the overall system. Click again. And what on the threshold, though, is the next generation. This is a picture of the Planet Labs, the cameras they have, the small satellites. These are producible. They're cheap. In this community, we can say they're cheap. We can't say that somewhere else because they cost $1 million maybe each or something. But they're mass-produced and they're usable. Can they be used for us? Go ahead and click a picture. I thought this was an interesting image because it gives you an idea of the scale of old technology. Sorry, ISS folks here, it's old technology divine, but that's a space station and these little satellites coming out. So the capability of these little satellites is great in some areas, but maybe not suitable for us. But they're there, and we're going to see, click one more time on this, we're going to see constellations of small sats available. What can we do with those? We can't, it won't solve everything. We have that backbone system we're going to have, but we're going to have to see maybe microwave radiometers can be fit into a small sat. Maybe a constellation of these, not constellation managed, but just free drifting around the orbit, could be a solution, and we have to figure out how we deal with the data for that. So the combination of all three of these elements, the access to space, the data rights and provenance and utilization, and the satellite technologies, taken together as an integral system, really enable a much broader, much greater future. But any one of them alone is not sufficient. We have to have all three, and they all have to move forward at the same time, or you end up with a stool which has one leg which is really short, and that doesn't work very well. So my last slide then, go back to the starting point, was what we had, what is on the cusp of something. A transition often comes up with an explosion of some kind. An explosion of capabilities, of possibilities, but an explosion. You want to benefit from it, ride the wave and not be consumed by it. And if we're not careful, we may end up, we have to make sure that we're not consumed by the explosion and end up being irrelevant. And we want to ride the wave going forward. And that's it. Thank you. time for a couple of questions, or do I not? Okay. Okay. Or not. Or you can just enjoy your desserts. Oh. The DMSP that recently went dead was one of the ones, so the proposed, and I think the DMSP both, are non-maneuverable, non-deorbitable, so they were built before we had the deorbit requirements. I would say that the environment, the contamination and the debris environment is just getting worse up there. I still think that the relative the loss of one satellite versus another, when you consider the 80 to 90,000 larger than 10 centimeter particles we're already tracking, is relatively small. And all of the satellites we launch now are maneuverable. We track them and we move around them on a regular basis. So I don't think the loss of a satellite is really, unless it explodes, and there was a little bit of debris cloud potentially that came from that, is really going to make a major contribution. There's enough noise up there already and junk up there already that we already are. I wouldn't say it's a high risk, and my personal perspective is we have to be aware of it. We have to protect our satellites and be ready to maneuver around them when we see them. But we haven't lost, the relative risk of losing a satellite to debris is small compared to the just aging and failure of components of the satellites. That's just history. Hasn't led us to, haven't lost many that way. Down in front.
Hey Steve, how many nations now have their own weather satellites, and then what percentage of those do we collaborate with?
I'm probably going to fall back on my 4 months at NESDIS now and say I don't know. We collaborate with many. We use data obviously from the Europeans, from EUMETSAT, from the Japanese. We look at data on a provisional basis from the Indians. We evaluate data from many other places, including we look at the data from the Chinese and the Russians, but we don't ingest it. We don't utilize it in any kind of formal fashion. So we look at many data sets, and there are individual nations which have them as well. So there are probably many more, and the Koreans actually, should add the Koreans as well because they're getting ready to launch them. So we have formal arrangements with several, with the Europeans and with the Japanese, and I probably should check and see. I'm sure there are others that I'm not aware of. There's in the back there.
There's been a fair amount of press in the last few months about the possibly impending gap based largely on the GAO report. Your flyout charts seem to say the sky is not healthy. So can you please tell us how healthy SNPP and those constellations that are up there now are?
Right. So it goes back to what you consider. What do you prepare for? I prepare for a satellite that has a 7-year lifetime, and I have fuel with margin. And the fuel with margin could make it last 10, depending on the quality of my orbit insertion. If I get a good orbit insertion, I may have 15 years of fuel. So you saw in those charts fuel-limited lifetimes. That means, barring anything else, the satellite should be up there and operating for 10 to 15 years. However, as the previous question from Frank over there about orbital debris, we could lose a satellite today from an orbital debris that we couldn't measure. We could lose a satellite at launch because it's a 99% probability to be successful, which means 1 in 100 is not going to work, potentially. So you prepare for a failure even though you don't expect it. It's like having airbags and you're not going to drive crazy because I got an airbag. What the hell, I'm going to crash? I don't care. You don't expect to have a crash, but you're going to have seat belts and an airbag. I don't expect to lose a satellite, but I got to prepare for it if it happens because the impact of it happening is sufficiently severe to the nation that we need to have a backup. So the gap we have is a potential gap, not a guaranteed gap. So sometimes you see me report we will have a gap in March of 2015. We're not going to have a gap unless they see debris that I haven't seen yet. It's not going to happen. But it could happen because we're no-fault tolerant. If I lose SUMI NPP right now, there's capabilities on there that I have no redundancy for. So there are measurements which we will not have ready solutions. If I lose POEs, I have SUMI NPP. So as long as we're no-fault tolerant, it can take any failure, which I can probabilistically say it's not likely to happen but could happen, and I'm in a bad situation. So that's why the gap is closed from our perspective when we are one fault tolerant. We can lose a satellite and still have full capability. And that's the objective we're trying to achieve both in the GOES satellites where we have right now, and the polar orbiting satellites. So when J1 launches, we will be, and we'll have SUMI NPP, we will be one fault tolerant with an aging SUMI satellite. As you go towards the end of that, it's going to be 10, 11, 12 years into its cycle. So then you start to get nervous. That's why we need to have 2 relatively healthy birds up there to be single fault tolerant, which is our objective.